What precisely lies at the edge of the discernible universe? This has stayed a secret for quite a long time, energizing interest and theory among researchers and fans alike. However, the James Webb Space Telescope holds the key to revealing this vast secret with its powerful capabilities. It has recently made a historic declaration about what lies at the edge of the recognizable universe. When we discuss the edge of the universe, it's essential to understand the concept of the detectable universe. The detectable universe includes everything we can see, measure, and study from Earth or our space-based telescopes and exploratory tests. Currently, it comprises stars, galaxies, and other celestial objects that are within our observational reach. So what's the difference between the universe, with a capital U, and the recognizable universe? In basic terms, the perceptible universe is only a small part of the whole universe that we can study and grasp, while the total size and shape of the entire universe remain obscure. There is an estimated width of the perceptible universe, which is around 93 billion light-years. A light-year is a unit of distance that light travels in 1 year, about 5.88 trillion miles or 9.46 trillion kilometers. Thus, the breadth of the perceptible universe, 93 billion light-years, is an incredibly immense territory, spanning roughly 5,468 billion trillion miles. This universe is expanding at an increasingly faster pace, driven by confounding forces like dark energy. As the universe expands, particles of matter begin clustering together due to the force of gravity, forming or inspiring structures such as stars, galaxies, and eventually even planets like our dear Earth. Over endless years, these infinite designs became larger and more complicated, leading to the extraordinary diversity of objects and phenomena we observe throughout the universe today. Despite the vastness of the universe, it is predominantly void. To put it in context, if we scaled down our entire solar system to the size of a quarter, the closest star would still be the distance of 2 soccer fields away. And this is just within our Milky Way galaxy, which is one among billions in the recognizable universe. You might ask, why can't we see the whole universe? There are 2 factors that explain this. The first reason is that light takes time to travel through space. When we look at distant objects in the universe, we are actually seeing them as they were in the past. The farther away an object is, the longer its light has taken to reach us. So by observing far-off galaxies, we're essentially looking back in time, unraveling the history of our universe. The second reason is the universe's expansion. Imagine spots on the surface of an expanding balloon. As the balloon grows, the spots move away from one another. A similar principle applies to the universe, where galaxies are receding as space itself expands. This expansion causes the light from distant objects to stretch, moving towards longer wavelengths, which we observe as redshift. Eventually, some objects will move beyond our observational reach as they retreat past a specific distance. Considering these factors, it's not surprising that we haven't seen the entire universe yet. However, the concept of the edge of the universe is a fascinating point that has intrigued researchers, philosophers, and thinkers for many years. We have various hypotheses about what lies beyond, but reality remains elusive. There are 3 standout hypotheses. The universe continues endlessly. This hypothesis is based on the cosmological principle, which states that the universe is isotropic, meaning it appears the same in every direction. If this principle holds true, it suggests that the universe extends indefinitely without a limit. The universe is finite but unbounded. This implies it's like a giant sphere. If you continue in any direction, you'll eventually return to where you started. The multiverse hypothesis. This proposes that our universe is just one of many. Imagine a multitude of parallel universes, each with its own set of rules and properties. These universes could be entirely different from one another or somehow connected. Now that we've explored the ideas surrounding the edge of the universe, let's turn our focus to a remarkable tool that has the potential to shed light on these secrets, the James Webb Space Telescope, JWST. This incredible telescope allows us to look far back in time and discover unexpected objects from the early days of the universe. The JWST, with its advanced capabilities, has empowered astronomers to peer back into the universe's infancy and ponder its mysteries. In a recent study published in the journal Nature, the JWST discovered 6 massive galaxies that existed between 500 million and 700 million years after the Big Bang. Scientists were only hoping to find small, newly formed galaxies, but the JWST caught them off guard. These galaxies are much larger than anyone ever imagined, challenging what we thought we knew about the early universe. Moreover, researchers found something astonishing: these galaxies are as mature as our 13-billion-year-old Milky Way. The mass of stars within each of these galaxies totals several billion times that of our Sun. According to the research, one of them may be as massive as 100 times our Sun's mass. For comparison, the Milky Way contains a stellar mass comparable to about 60 billion suns. The JWST has exceptional power. It can see things that are invisible to our eyes by utilizing infrared light. It captures the faint glow from ancient stars and galaxies that have been around for a long time. This means the JWST can literally take us back in time, providing a glimpse of what the universe looked like around 13.5 billion years ago. Now, here's where it gets truly fascinating. The universe is estimated to be around 13.7 billion years old, so this discovery has flipped things upside down. It's like rewriting the history books. These massive galaxies, nicknamed universe breakers, have researchers scratching their heads. They characterize close to 100% of the models we had for early galaxies. We used to think galaxies began as little billows of stars and dust, bit by bit developing over the long haul. Well, these universe breakers refuted us. At the point when the Webb data and high-resolution photographs from the telescope became accessible in July 2022, scientists were blown away. They were shocked when they saw these galaxies as critical marks of light, questioning their own interpretation of the data. The abrupt appearance of these giant objects astonished everybody. By utilizing spectroscopic techniques to investigate light across various frequencies, researchers can reveal important data about these galaxies, such as their composition, size, and distance from Earth. Interestingly, this wasn't even on the list of heavy discoveries scientists hope to find with the James Webb Space Telescope, JWST. It surpassed all expectations and unfolded much faster than guessed. There's even a chance that some of the objects tracked down using JWST data might be something else. While most are likely galaxies, there's a chance that a couple could be hidden supermassive black holes. Meanwhile, utilizing the powerful James Webb Space Telescope, an international group of cosmologists made an incredible discovery. They found the oldest and farthest galaxies of all time, confirming these systems date back to when the universe was only a fraction of its current age, less than 400 million years after the Big Bang. The light from these galaxies reached us more than 13.4 billion years ago, as identified by the telescope. Like the early observations made by the Hubble Space Telescope, the initial images captured by the JWST revealed various potential galaxies. Now, through MEDIC spectroscopic observations, cosmologists have confirmed many of these objects, allowing them not only to study the physical properties of the galaxies but also to accurately determine their distances. To determine a galaxy's distance, space experts calculate its redshift. You might be wondering what redshift is. Well, as the universe expands, objects seem to move away from us, causing their light to stretch and shift toward longer, redder frequencies, a phenomenon known as the Doppler effect. While redshift estimates can be obtained from photographs taken through different channels, spectroscopy is the preferred method for acquiring accurate measurements, as it separates the object's light into its constituent frequencies. The new discoveries center around 4 galaxies with redshifts greater than 10, which means they are extremely far away. The Hubble Space Telescope had previously spotted 2 of these galaxies, and their redshifts were confirmed to be 10.38 and 11.58. However, the JWST images revealed 2 significantly more distant galaxies with redshifts of 13.20 and 12.63. A redshift of 13.22 indicates a time roughly 13.5 billion years ago, uncovering ancient cosmic history. Additionally, the JWST's Advanced Deep Field Study, JADES, is an ambitious program that has been allocated over a month of the telescope's time. Its objective is to provide a remarkable, in-depth look into the early universe. In 2015, a consortium of instrument groups proposed this project, forming an international collaboration known as JADES, which includes over 80 astronomers and researchers from 10 different countries. Starting with NIAM, the JADES program dedicated 10 days of mission time to observing a small region of the sky, including the Hubble Ultra Deep Field. For more than 20 years, cosmologists have been investigating this area using various large telescopes. By concentrating on the field in 9 different infrared frequency bands, the JADES group made an exceptional discovery of almost 100,000 distant galaxies, each billions of light-years away. Next, utilizing the NIRCam spectrograph, the researchers gathered light from 250 faint galaxies during a 3-day observing period. This enabled them to uncover the attributes of the gas and stars within these galaxies and obtain precise redshift values. With these measurements, astronomers can determine the intrinsic brightness of the galaxies and estimate the number of stars they contain. This allows for an extensive assessment of galaxy development over time, even without direct information on their initial development stages. Examining galaxies can be as challenging as understanding human beings. The early ages of stars have a significant impact on the future of galaxies, much like how our initial experiences shape our lives. This is an unprecedented time in history when the extraordinary capabilities of the Webb telescope are answering various questions about galaxies. NASA's Deep Space Observatory is altering our comprehension of the universe and revealing a treasure trove of new discoveries. The James Webb Space Telescope, JWST, a trailblazer in scientific research, is furnishing us with astonishing insights into galaxies, planets, stars, and other captivating astronomical phenomena. Launched in December 2021 and expected to operate for 2 decades, Webb is just embarking on its astronomical journey, outperforming the standards set by its predecessor, the Hubble Space Telescope. JWST has captured the imagination of researchers and the public alike, inspiring a wave of scientific excitement. People around the world are eagerly analyzing the telescope's raw data, sharing its stunning photographs, and gaining new perspectives. Following a flawless deployment process, Webb amazed us with its initial images in mid-July, granting us an extraordinary view of our universe's vastness. With the help of its advanced infrared telescope, we can explore the farthest galaxies in astonishing detail and peer into the depths of the past. Shortly after going online in late June 2022, Webb's powerful instruments began uncovering thousands of previously obscure galaxies, older and more distant than anyone had ever imagined. Moreover, the telescope's capabilities empower researchers to gather ample light from celestial objects, such as exoplanets and infant stars, revealing their compositions and tracking their trajectories through space. This wealth of data is already revealing intricate insights about the atmospheric structures of planets found hundreds of light-years from Earth, suggesting their potential habitability. Additionally, by analyzing faint hints of light from the universe's early stages, the James Webb Space Telescope has possibly identified the oldest black hole ever seen. This supermassive black hole, with a mass 9 million times that of the Sun, resides at the center of a young galaxy that formed just 570 million years after the universe's inception. Thanks to Webb's powerful cameras, we can look back in time to the universe's earliest moments. Amazing revelations offer bits of knowledge into the astronomical daybreak when various dark openings filled in size throughout the span of 1 billion years following the Big Bang. The origins and expansion of these baffling astronomical substances remain secrets that riddle space experts. Some of these gigantic infinite disturbances emit light recognizable by telescopes, produced by the contact of materials spiraling into their gravitational chasms. These objects, known as active galactic nuclei, AGN, supermassive black holes, or quasars, are billions of times more massive than the Sun, transmitting extreme explosions of light trillions of times more brilliant than the most brilliant stars. They represent the most outrageous type of AGN. As researchers delve further into the universe, they can capture light from more distant sources, giving insights into earlier phases of the universe. The James Webb Space Telescope, JWST, utilizes its mid-infrared instrument and near-infrared camera to filter the sky, searching for black holes. Its inherent spectrographs then separate the light spectrum into various frequencies, allowing researchers to analyze the data. During their examinations, researchers made a significant discovery: the heated material surrounding a black hole emitted faint hints of radiation across the universe. By studying these fragile glints from the universe's outset, they identified a surprising flood among the frequencies embedded within the light, providing significant insights into the grandiose cycles at play. The rapid emergence of black holes in our young universe remains a mystery. Researchers continue their quest for much younger primordial black holes, believed to have formed just after the Big Bang, or perhaps even earlier. However, these elusive objects have yet to be found. Meanwhile, two primary explanations exist for the abundance of black holes in the present universe. One possibility is that they are remnants of massive stars that formed much more quickly than the stars we observe today. Alternatively, it is suggested that dense clouds of gas suddenly collapse to form these mysterious singularities in spacetime. A more likely scenario involves population 3 stars, a speculative class of stars that emerged around 200 million years after the Big Bang, primarily composed of hydrogen and helium. Such a star would have exploded, leaving behind a black hole. Therefore, the black hole would have grown in size by rapidly accumulating matter at a rate surpassing stability. Researchers are collaborating with the team behind the development of the mid-infrared instrument, MIRI, to study distant cosmic sites and gather additional clues about the formation of the mysterious black hole at its center. They have also examined the early stages of the universe and observed the development of a protocluster comprising 7 interacting galaxies. This group, discovered by the Hubble Space Telescope, is the most distant galaxy cluster identified by scientists. Simulations suggest it will ultimately become one of the oldest and largest known galaxy clusters in the universe, with a mass nearly 100 times greater than that of our Milky Way galaxy. While the initial discovery of these galaxies was made by the Hubble Space Telescope, it lacked the precision to accurately measure the distances between them, despite their arrangement along the same line of sight. Imagine being high above Los Angeles and looking through a telescope. You could see Phoenix, Dallas, and Atlanta, but you wouldn't know the exact distances separating them. However, thanks to the James Webb Telescope, we have gained a much clearer picture. These types of clusters, according to researchers, are quite rare and difficult to find. Although it is unlikely that the JWST will discover another intriguing system like this, the upcoming Nancy Grace Roman Space Telescope, set to launch in mid-2027, will enhance our ability to identify galaxy clusters in the early universe. Its wide-area survey capabilities will surpass the JWST by more than 100 times. Returning to the discoveries made by the JWST, during the 1990s, astronomers made significant exoplanet discoveries due to this revolutionary telescope. We now know of over 3,000 exoplanets, although only a dozen have been directly imaged. Most exoplanets are so distant that we can observe them when they transit in front of their host stars, causing a slight dimming of light. However, the JWST has changed the game. Using the telescope's coronagraphs, combined with its cameras, filters, and other equipment, researchers can directly observe exoplanets. In 2017, the Circle Consortium made a significant discovery by identifying a planet called HIP 65426b using the Spectropolarimetric High-Contrast Exoplanet Research (SHERLOC) instrument. HIP 65426b is an exoplanet that orbits its host star HIP 65426. In September 2022, it gained further attention as the first exoplanet to be directly observed by the James Webb Space Telescope. What makes this planet particularly fascinating is its remarkable attributes, combined with the astonishing sensitivity of the JWST, which allows for clearer observations. Unlike any other planet in our solar system, HIP 65426b is located at a distance from its host star that is more than 20 times greater than the distance between our Sun and Earth. To put this in perspective, Pluto is just 39 times farther from the Sun than Earth. Now imagine an exoplanet that is a massive gas giant, 6.9 times the size of Jupiter. Although this distant world is elusive in the night sky, its brightness is still noticeable, especially when captured by Webb's infrared camera. When we observe the galaxy known as M74, we are treated to a stunning view of its beautiful spiral shape and the scattering of stars. The galaxy's brilliant center gives rise to arms that stretch outward. Hubble's optical view of this object highlights its clarity, revealing structures resembling heat-emitting dust and gas filaments radiating from a brilliant center, all depicted in a striking electric blue. In the image captured by Webb, we see the brightening of star-forming regions dispersed throughout the spiral arms. Thanks to its infrared capabilities, combining images from the Hubble Space Telescope and Webb, scientists have created a stunning composite picture. This composite features both the optical and infrared views of the galaxy, providing a more complete understanding as part of a global project. These three images were highlighted in a film, allowing astronomers to examine them side by side. Through this process, they were able to identify regions where stars are currently forming and gain accurate measurements of star cluster masses and ages. Furthermore, Webb studies have provided valuable insights into the characteristics of tiny dust particles traveling through the vast expanse of interstellar space. Webb also captured an image of a distant Wolf-Rayet star, which displayed a remarkable diffraction pattern. The star, known as WR140, is surrounded by a wave-like arrangement of concentric rings, giving it a strangely square-shaped appearance. Surprisingly, these distinctive ring arrangements are not imaging artifacts, but real characteristics of the star. These massive stars are reaching the end of their life cycles and have already expelled a substantial amount of hydrogen into space. The interaction between WR140 and its smaller companion star creates a dust storm that shapes their neighboring star, resulting in the unique ring structures in the celestial body. The most widely studied exoplanet outside our solar system, WASP-39b, orbits a star located an astonishing 700 light-years from Earth. It is a scorching gas giant, nearly the size of Saturn, orbiting its host star at an incredibly close distance, approximately 1.3 times closer than Mercury is to the Sun. Finally, the JWST was designed to venture to the farthest reaches of the universe, and scientists have confirmed its success in doing so.